Next, we'll look at the Fibonacci sequence. The Fibonacci sequence, F0, F1, F2, is defined by the initial conditions F0 equals 0, F1 equals 1, and the recurrence relation Fn equals Fn minus 1 plus Fn minus 2. Simplified, that is, Fn is the sum of the two previous terms of the sequence. And this is 4, n is equal to 2, 3, 4, and so on. Next, we'll find F2, F3, F4, F5, and F6, the terms of the Fibonacci sequence. To find F2, that will be equal to the sum of the two previous terms. So that would be F1 plus F0. Substitute in the values for F1 and F0. F1 is 1, F0 is 0. That gives us the total of 1. To find F3, that will be F2 plus F1. F2 was 1, and F1 was 1, giving us a total of 2. F4 is equal to F3 plus F2, giving us 2 plus 1, numbers 3. F5 is equal to F4 plus F3. F4 was 3, and F3 was 2. So now we have 5. And lastly, we want to find term 6. F6 is equal to F5 plus F4. So this is 5 plus 3, and the number is 8. And you could keep going, and you'll notice that the pattern starts growing slowly, but as it gets a few terms into the sequence, it starts to grow at a very rapid pace. The Fibonacci sequence occurs frequently in nature, in everything from flower petals to population growth, to the bone sizes in your fingers, to the spiral in seashells. It is also the basis for the golden ratio, which is used widely in architecture. Let's take a look at an example. Suppose that sequence an is the sequence of integers defined by an is equal to n factorial. The value of the factorial function at the integer n, where n is equal to 1, 2, 3, ... Because n factorial is equal to n times n minus 1 times n minus 2, ... down to 2 times 1, that simplifies to n times n minus 1 factorial, which simplifies to n times an minus 1. We see that the sequence of factorial satisfies the recurrence relation an equals n times an minus 1, together with the initial condition a1 equals 1. We say we have solved the recurrence relation together with the initial conditions when we find an explicit formula, called a closed formula, for the terms of the sequence. For the next example, determine whether the sequence an, where an is equal to 3n, for every non-negative integer n, is a solution for the recurrence relation an is equal to 2 an minus 1 minus an minus 2, for n is equal to 2, 3, 4, and so on. So to solve this, we'll start by substituting in our 3n. That's that an is equal to 3n. And we want to be careful not to confuse with the subscript on your a's. So your a, n, n minus 1, those refer to an element in the sequence. Don't confuse that for the value of those elements. That's one of the common mistakes here. So we'll substitute in. We get 2 times 3 times, and then this would be n minus 1, minus 3 times n minus 2. We'll multiply this out, get 2, 3n minus 3 minus 3n plus 6. Then we'll multiply one more time. We get 6n minus 6 minus 3n plus 6. The 6's cancel. Subtract the 3's, and that gives us an equal to 3n, which means, therefore, this is a recurrence relation for an is equal to 3n. Suppose we have the same question as above, with n being every non-negative integer, and an is equal to 2 to the nth power this time. Is this a solution to the recurrence relation? To determine if it's a solution, let's first find the first few elements for our an equals 2 to the nth power. So let's find a0, because that's a non-negative integer. Okay. 1. A1 is equal to 2. A2 is equal to 4. And then we can take a look at those plugged into the initial problem. So we had 2 an minus 1 minus an minus 2 plugged into that problem. It gives us 2 times a1 minus a0. Plug in our values, we get 2 times 2 minus 1, which is equal to 3, which is not equal to our a2 element, which was equal to 4. And again, we took the a2 element here, and we're plugging that in there from the start. So our a2 elements do not match. Therefore, this is not a solution. Many methods can be used to solve recurrence relations. Iteration is a useful and straightforward method. For an example, we'll solve the recurrence relation an that satisfies recurrence relation an is equal to an minus 1 plus 3, for n is equal to 1, 2, 3, and so on, with the initial condition a1 equals 2. And we'll do this using forward iteration. So for element a2, it will be 2 plus 3. 2 was the value for element a1. Then for element a3, it will be equal to 2 plus 3 plus 3. And we can look at that and go, oh, okay, well, essentially that's the same as saying we've got 2 plus 3 times 2. And then we can look at a4 and say that is everything from a3, which was our 2 plus 3 plus 3, and then we add 3 to that. And if we rearrange this, it gives us 2 plus 3 times 3 this time. And notice each time we go down a line, we are adding 1 to the number of 3's that we multiply. And that adding 1, it looks like has another relation for us here. In the A3 line, the number of 3's that we're multiplying is 2, and that is our iteration in the term sequence, A3 matches that 2 as a 3 minus 1, right? So for the next line, for A4, well, we're multiplying 3 3's there. Again, that matches. That's n minus 1. So as we iterate this series down forward, we have an is equal to 2 times 3. Actually, pull that 3 to the outside here, and we'll go n minus 1. That way we have the number of 3's we're multiplying by is the number element in the set minus 1. And this forward substitution method of iteration allows us to see these patterns and develop a formula quite easily. You can also substitute backwards. So we'll start with an is equal to an minus 1 plus 3 and work backwards. So the previous term before that would have been an minus 2 plus 3 quantity plus 3, which if we rewrite and simplify gives us an minus 2 plus 3 or plus 3 times 2 because there were 2 of them. And we go to the previous term before that, an minus 3 plus 3 plus 3, and if we expand that out, it gives us an minus 3 plus 3 times 3, and we generalize this as we work down towards the beginning, getting to element A2 plus 3 times n minus 2 is equal to A1 plus 3
times n minus 1,
which is equal to 2 plus 3 times n minus 1.